Welcome! Today we're going to build a clear, intuitive picture of chemical thermodynamics. We'll cover systems and surroundings, work, heat, energy, state functions, the first law, enthalpy, Hess's law, and a short intro to entropy and Gibbs energy for spontaneity. Let's start with the most important idea, the system and the surroundings. The system is the part we're studying. The surroundings are everything else. The boundary separates them. We classify systems as open, closed, or isolated. Open systems exchange both mass and energy. Closed systems exchange energy, but not mass. Isolated systems exchange neither. Energy transfers between system and surroundings mainly as heat and work. Heat flows because of temperature difference. Work is organized energy transfer, like pushing a piston. We use the sign convention. Heat into the system is positive, and work done by the system is positive. Properties can be extensive or intensive. Extensive properties depend on the amount of substance, like mass, volume, or total energy. Intensive properties do not, like temperature, pressure, and density. A state function depends only on the current state, not the path. Internal energy, enthalpy, entropy, and Gibbs energy are all state functions. Now, the first law of thermodynamics: energy is conserved. The change in internal energy equals heat added minus work done by the system. Enthalpy is defined as H equals U plus PV. It's useful because at constant pressure, the heat transferred equals the change in enthalpy. Heat capacity tells how much energy is needed to change temperature. Specific heat is heat capacity per unit mass. We measure changes in U and H using calorimetry. For reactions, enthalpy changes can be combined using Hess's law. The total enthalpy change is the sum of enthalpy changes of steps. This lets us build reaction enthalpies from known data, like bond dissociation, formation, combustion, atomization, sublimation, phase transition, ionization, solution, and dilution. Now we introduce entropy S, a state function that measures how energy is spread out. The second law says the total entropy of the universe tends to increase. Gibbs free energy tells us if a process is spontaneous. Delta G equals delta H minus T delta S. The sign of delta G gives us spontaneity. If delta G is negative, the process is spontaneous. If delta G is positive, it is non-spontaneous. If delta G is 0, the system is at equilibrium. That was a fast, visual tour of chemical thermodynamics. The key idea is energy conservation, energy transfer, and how entropy and Gibbs energy predict spontaneity and equilibrium.